So this talk is called the Canvas API for Rubyist. So who am I? My name is Dean Hudson. I work at a place called Massively Fun. I'm a senior developer there. I do HTML5 gaming. So Massively Fun makes games with open web technology. We're hiring. We do a lot of cool stuff, and a lot of it's client-based and a lot of it's server-based as well. You guys may have seen this game. It's called Words Squared. Has anyone seen this? Yeah? Yeah? It's pretty rad. It's basically a giant, I want to say, tile-based crossword game, because I'm not allowed to use certain words. That's built on an infinite board. So basically, you can play asynchronously, massively multiplayer, play this crossword game, and every tile that gets played on the board is part of this world, this massive word that should not be mentioned board. And so right now we have about 200 million tiles. It's a pretty big, epic sort of thing. You should take a look at it. People do things like put their initials in. They go off into space. So if you take a look at this, I wish I could say I was more involved with it, but actually it's mostly the work of my boss, Grant. And it's a pretty fantastic thing to look at. So that's one of the things that we do. We're working on some other stuff, too, that I'm not supposed to talk about. So what is this talk? This talk is actually a little bit less about the Canvas API and more about the patterns in which it can be used. So I've actually lied to you twice. I said this is Canvas. I've said it's for Rubyists, and we're doing no Ruby and actually kind of very little of the API. But what you can do is play along. So I'm actually going to talk about patterns that we use as game developers, kind of a simplified version of these patterns that we use as game developers to put things on the screen and kind of interact with objects in the Canvas API. So I had this idea that I wanted to, like in the spirit of like Ruby cones, I wanted to do like Canvas haiku. And so I started doing some of this talk as haiku, and it ends up being really challenging. The API calls tend to have a lot of syllables, so fitting them into 575 is kind of hard, but there's some terrible haiku that's left in this talk, and I apologize in advance for that. The URL there, if you see it, if you want to play along, that's got a version of kind of a really simple infrastructure that's like the one I'm talking about that you could play with, and you can actually build your own game entities and kind of your own drawing primitives and put them on the screen. So if you want to play along, that's where to do it. So here we go. Canvas API, 2D graphics in browser. It is quite simple. That's haiku, by the way. So Canvas is a 2D immediate mode graphics API. It's well supported in modern browsers. Basically, it's a bag of draw calls. And what you can do is you have a Canvas element, you put it into your HTML document, and you can grab the context and draw to this thing. It does really nice animation without Flash, and so that's kind of one of the key features. And so you actually have support on mobile. In Mobile Safari supports it well. On Android, it's not as well supported, but things are getting better. So this is kind of an example. I put this up here. For testing purposes, I needed to stub the Canvas API. And so I just want to get into your heads that this is actually a really small thing. You can learn this API relatively quickly. So if you look at this, plus this, plus this, plus this, and that, those 4 or 5 pages actually represent all the calls that are made that basically exist in the API. So this is a stubbed out version of the Canvas API that I use for headless testing. And you can see on 4 pages of code, you've got about 38 calls or so. And that's pretty much all you need to know. You can learn this thing in a weekend. It's not that hard. So the Canvas context, this is kind of the key thing that you're going to use when you're using Canvas. It's this is the haiku. I should get back to that, I guess, huh? The Canvas context, it has all the calls to draw the pixels to the screen. This is really simple. So once you have an element that is a Canvas element, you can just do a basic document get element by ID. assuming that you've got this thing, it's actually got an ID that's canvas, because otherwise that call will not work. Get context 2D. So maybe you've seen this elsewhere. Who's used Canvas? How many people have actually played around with this stuff? It's a good number of you have. This is just the very basic stuff. So get context 2D actually puts you into a 2D mode where you actually have access to the 2D graphics calls. If you wanted to do 3D stuff, you would actually use a WebGL there. We're not talking about that. It's not well supported. In the future, in a happy future, it will be well supported, and we'll be able to do nice 3D games in all the browsers. So once you have this context, this is what we care about. You can do all your calls on that thing. So here's just a simple fill text that just puts text on the screen. From here on out, I'm just gonna reference this context thing because that's really usually what we care about. There are some other calls, like for measuring text, there are some other objects and things like that that can be handy, but this is really what most of your work is. This is where most of your work is done. So again, I think my slides got placed out of order, but we can learn this in a weekend. This is just me grepping that stub. It's about 38 lines. 38, the prototype is where I'm actually finding the method definition. So there's about 38 methods in there. It's not too hard to learn. We can learn the API, the draw API, in about a weekend. So we're going to actually move on to bigger things. And what I want to talk about are kind of the event loops and the cycles in which you're doing this drawing. So to the haiku, browser event loops are not well suited for games. You must roll your own. Did anyone here used to work in Perl for a long time? All right, so maybe you're with me on the haiku. We'll see. So here's a simple game loop. Kind of the idea here is you've got a collection of things. You're going to, on every tick, you're going to do these three things in a real broad sort of sense. So you want to handle your queued UI events and server events. And this is kind of important. If you're doing games or you're doing any sort of real-time graphics stuff, you do not want to handle user like UI events and server events just you don't want to handle them right when they come in. You want to queue them up as the stuff comes in and then handle them in a controlled part of your event loop. Otherwise, you are going to get all sorts of performance issues. So once you do that, at the start of your loop, you're handling those events. That's changing the state of your screen, whatever's happening in your game, your visualization. You're going to update the state of things. I'm using things in quotes for now because we'll get into what those things may or may not be. And that's basically, if an object has its own behavior, do that now. Then we're passing everything that's changed into some sort of renderer or some sort of draw call and redrawing all the things. All of the things. So here's a really fake game loop. So I'm going to apologize. Again, this is my no Ruby apology. This is CoffeeScript. I have a love-hate relationship with CoffeeScript. I like it when I can put it on a slide like this because it's very succinct and nice. Sometimes I really hate it, but we'll not get into that right now. So this is just a real simple game loop. It has a run, right? So we're going to call this run call. And this really basically handle the queued events, update the things, draw the things, and loop somehow. Anyone who's done a decent amount of JavaScript knows that these are kind of your go-to guys. Set interval, what that does is that basically you give it a callback and it will call that function basically on a timer, so every 16 milliseconds or so, or set timeout, and in that case, you would actually set timeout will call a function once, and then you give it a time, like say 16 milliseconds in the future, and that function has to refer to itself and call itself again with its own set timeout. So these are kind of the traditional ways to do this, and I want to encourage you to do neither of them. What we have issues with, we have timing issues when we use set timeout. And first of all, set timeout is the better way to go versus set interval if you're going to use one of those two things. But set timeout does have these issues. And what happens is when you're trying to run 60 frames per second, that's 60 over 1,000 milliseconds, you get this 16.666666666, and forever until you run out of digits. That doesn't quite mesh with how your browser works. Your browser timers actually end up on whole milliseconds. So when you're doing, say, a set timer, you can choose between 16 and 17 milliseconds. And that, for the most part, will work, except for when you actually, that 1 millisecond starts to add up, right? And so say you're 20 frames in, you're going to see some frame skips as you get deeper into this, this application. And that looks like crap. It ends up being non-smooth animation. It's not what you want. So I'm going to discourage you from using set timeout. Another quick aside, I don't know if you guys have the Canary or the dev builds of Chrome. If you do, and you're doing this type of work, this is fantastic. They've got a new feature in the timeline that handles frames. It'll actually tell you how long each frame is. It'll tell you where you're spending your time. It's worth looking at if you're into this animation sort of stuff. For accurate loops, request animation frame will bring you great joy. And the greatest thing about this, Haiku, is that request animation frame is all 7 syllables. So I got the whole thing. I couldn't fit a single, like an extra syllable into that middle line. It's kind of amazing, which is why the Haiku were a little bit challenging. So, has anyone here used the request animation frame? You guys familiar with it? A few of you have. This is, I wouldn't want to, I hate to say the words the new hotness, but it's newer and it's hotter and it's much better to use if you're doing animation stuff than set timeout or set interval. So what request animation frame does is it allows the browser to manage the screen updates efficiently. And so what you do in this case is you say, hey, I've updated something on the screen. I want you to re-render this, but I want you to do it when it's the best time for you. So the browser then organizes itself, and it talks to the GPU, and it will put bits on the screen at your actual refresh rate, which is much better than just trying to throw them out willy-nilly with your set timeout. So this is the way to go. If you take one thing away from this talk and you're doing animation stuff, this is the thing to take because it really makes a huge difference. And it actually also uses more accurate timing. So now, in this sort of world, we have in newer browsers, from Chrome in particular, and I think it's happening in the other browsers, we're getting higher resolution timers. And the newer builds of Chrome actually use high resolution timers with request animation frames, so you can actually get real accurate timing with your animations. Unfortunately, request animation frame is not uniformly supported in browsers, so you need to work your way around this. And a lot of you guys are probably web developers, have done the JavaScript sort of thing. We need to build a polyfill. You can Google this. If you just Google request animation frame polyfill, this is just kind of your backup plan, right? So basically, if the browser actually implements request animation frame, you're good. Go for it. Awesome. Otherwise, let's see if it implements WebKit request animation frame. Otherwise, let's see if it implements Mozilla's web request animation frame, and so on. Until we get to the end, if none of these things are true, we do fall back onto set timeout. And so this is real simple. You pass it a callback, and it does the 1,000 over 60, which is just going to actually round it down to 16 milliseconds. So using this will allow you to call request animation frame whether or not your browser supports it. Again, just Google request animation frame polyfill, and you're all golden. So let's look at a game loop now. So this is, again, CoffeeScript, and this is a real basic, watered down sort of game loop. And this might be kind of like the core thing that you'd be looking at just to run your game. And so remember, in place of the browser's event loop, we're running our own loop because we want to handle our updates by hand and actually have pretty granular control of our animations. So real basic constructor in this case. I'm passing it a canvas element, and then I'm holding on to a canvas context, basically a context 2D, which I'm grabbing from the element. I'm keeping track of entities, which we'll get to in a second. Entities are things that are going to be managed by my game loop or kind of involved in my game or rendered to the screen or whatever we want to do. So just kind of holding on to those things, we've got a real simple way to add entities. We're just using an array for entity management now. There are all sorts of complex and interesting things you can do with entity management, but it's beyond the scope of this talk. It's a very simple run method. We call request animation frame. This is going to return an ID, and that's useful because just like set timeout, you get an ID back, which allows you to actually cancel this loop if things go haywire or you decide to stop or you don't want to animate anymore. So that's pretty important, and I'm just actually going to call that the tick because it'll be a unique number that's incrementing as we go. Next step. Step through my entities and make an update call on them. Next step through my entities and make a draw call on them. Real simple stuff, right? So the one thing to notice is that I am passing a tick into my entities update. That's for my sanity, because if I want to know if time has passed or if I'm in the future past, I can actually do updates based on this incremental tick that I'm keeping track of. The other thing to notice is that I'm passing the canvas context into the entity for the draw call. And this is just to kind of keep things nice and well-designed and simple so I can not have to have each of these things holding on to this canvas context with like a reference. And it ends up being kind of a nice thing for the API. So request animation frame returns an ID, and keep moving. So entities and recs. Entities and recs, the largest things are built from just these pieces. And so entities and recs are kind of the things that I'm talking about using in this game loop. And so these are the things that I'm going to animate to the screen. So a simple game entity does the following. It basically responds to the update call. So you saw in the loop, all the entities get update called on them. So if I want to move something, this is where it happens. Respond to that call. And you can manage position, height, width, whatever, because I want to keep track of what this thing is on the screen. I don't know if you remember, I said this is immediate mode. And you guys familiar with what immediate mode is? So with immediate mode drawing sort of context, that means that when you tell the computer to put a pixel on the screen, it just puts the pixel on the screen and forgets about it. If you want to have something that has a consistent graphic that you're moving around, you have to kind of manage all the drawing bits that are going to happen for that thing and kind of package it up in a way so I can move them all together and move things on top of each other, pull things out or whatever. So that's kind of why we're grouping stuff into this game entity. And then what I'm going to do is I'm going to delegate the draw call. So here's a real simple game entity. Constructor, I'm just keeping track of my XY position. That's pretty simple. Rect is about what we'll get to in a second. Update. When you subclass this, you will want to implement that, or else it won't do much. It'll just sit on the screen. Draw, and so this actually, I'm actually calling draw here. I'm delegating straight to the rect. And so what we're getting at is this is kind of a, this doesn't know anything about the actual drawing or canvas or canvas context calls. This is just a pure game logic sort of entity that knows where it is on the screen, knows how big it is, and manages kind of motion and things like that. Right there, delegate. I should actually be using the slides as I'm talking about the things that are on them instead of doing them out of order. So the simple draw primitive that we're going to talk about, this is our rect, and this is associated with an entity. And so what this does is this responds to the draw call and actually makes the canvas context 2D drawing call. So this will take a context, and it will say, OK, I'm a rect. Rect is kind of a funny thing to say, but basically, when you're dealing with these things on the canvas, they're going to be contained by a rectangle. So I like to call them rects because it kind of gets your head in the space where this is kind of a block that sits on the canvas. So this rect may be a circle, and hopefully that's not confusing. But you actually, in the draw call, that's where you would do the arc call to draw the circle. So if you want the thing to look like a circle, you make this rect in its draw call. It'll take that canvas context. It'll make the arc call, it'll draw the circle, and that's all it cares about. So the interaction with it and the entity knows where to put it and those types of things, but this just handles most of the drawing stuff. You also might want to do, there are some things that require intimate knowledge of the canvas context, particularly like pixel detection. If I'm doing hit detection with a mouse and I want to capture whether or not this has happened in a certain place, I actually need to know what the drawing primitive looks like and which pixels are colored, and so that type of thing ends up falling down into this layer as well. So here's a simple example, very, very simple again. This is a base class, so the draw call is unimplemented. But I'm just managing position. Again, it's kind of weird in managing positions in both places. What I usually do is I have a concept of like linking the position between these things. So an entity will actually link its position to the underlying rect, and then you just move one of them, and they both move. But this, again, has a draw call that takes canvas context and will do something fancy. Again, and another point that is worth making is that this is a really simple interface, and you can just duck type all you want with both these things. So like a lot of cases, what we'll do at work is we have things that are like UI controls. So we're making this elaborate user interface in Canvas, and we need to do things like buttons. And so we want to put a button on the screen, but a button's a bit different because it responds to events, and it's got these channels, and it's got to talk to other people. And so it's just different than a regular game entity, like something that would be like a Pac-Man on the screen. So we just implement the interface, duck type in like a UI control, and it can just drop right into our renderer and fire through. So here's a concrete example. The rect is, so I don't know. We use Stitch it, so I don't know if you guys are CoffeeScript, anyone? Maybe Stitch, maybe. It's just basically making this code look a little bit nicer and actually doing real requires, which is amazingly challenging in JavaScript. And no one can agree on how they want to do it, so that's what that is. But basically, this is a simple box. So you've got, this extends the larger, this extends rect, which is kind of your superclass, and you delegate, you don't need to do anything fancy in your constructor, but you do something in your draw call, which is a very simple canvas context 2D fill rect call. So this is like as easy as it gets, right? You're basically, this call just takes a rect, and it will just fill it with whatever color that the context is is stroking in right now. So it basically just fills a box, real simple. Da-dun, those things again. So canvas tests are hard, and the one true way to do this is to cheat. Canvas tests are hard. The one true way is to cheat. Stub the world. We had a lot of code that was using a lot of canvas calls, and it becomes very challenging to actually do TDD with this stuff because you need the browser, which means you need the DOM, and things just kind of become challenging. I know there are things like Jasmine, which I don't like. I think it's a big, heavy tool that's not necessarily my favorite. I've found that you can stub this stuff, and so that's what I've done is like actually stub the entire Canvas API, and then there are a few things that you can then use to kind of build your infrastructure. So JS DOM is a library that, do I have this? So this is actually the example from the above code that I showed you at the beginning. This is stubbed Canvas stuff. So you can use this with JS DOM, which basically is a pure headless version of the DOM that you can call from JavaScript. And what basically you do is you override the document create element call. So when you actually get a request for a Canvas object, you dump this fake Canvas object out, and you can just run your test really fast. So this works with Mocha, is what we've used it with, Express, like some of the Node, simple just test runners. Phantom.js is a thing? Or does anyone use this, or does anyone care? Do you guys even care about JavaScript? Okay, good. Yeah, Phantom.js is a thing, but it's slower, and it's kind of a pain. I don't know if anyone's gone through some of the trouble with it, but it does really crazy things. Like it communicates with your node process via an alert box that it's somehow parsing. It does some really gnarly stuff. So I think this is kind of the way to go. And I don't have this posted, actually, as open source, but I'll probably do that by this afternoon if you guys want to play with this testing stuff. I thought that I had a lot more going on, and I kept trimming my talk down. So I don't did I speak too quickly? Yes, no, maybe. Do you guys have any questions about any of the things that I'm talking about? Yeah.
So on the run little slide ages ago, you wanted to reason request admission frame.
Yes.
Call request admission frame first in the run loop.
Yes.
It seems like that could cause it. Well, I don't know. It seems strange to me.
That is strange, and I can actually go back to that slide because that's a really good question. And oh, sorry. So in this game loop, you'll notice that the first thing I'm doing in my run call is I'm calling request animation frame before I'm doing my work. And what that basically does is that gives you 16 milliseconds, right? So when this is being triggered, you're inside of one frame. And the first thing you want to do is trigger the call for the next frame and then do the work within 16 milliseconds. And that's the way you actually will be hitting your frames on time. Because what can happen is if your work pushes out to like 8 milliseconds or 12 milliseconds, you make this call, and then you hit the renderer in the browser, and that takes an extra 6 milliseconds, and it pushes you over, and you skip a frame. So you actually want to do that call kind of immediately.
So if your update and draw takes longer than 16 milliseconds,
you're screwed. Yeah. So if your update and draw takes longer than 16 milliseconds, you might want to look into having 30 frames per second versus 60, because you need more time in order to do your updates and your actual rendering. Yes.
You've got something at a higher level that's calling run as fast as it possibly can.
It's not calling run. So the question was, at a higher level, is this calling run as fast as it can? And so that's kind of the beauty of this, is it actually is only calling it once per refresh tick in the browser. So every time the browser's like going to do a redraw, just at a low level, the browser's got pixels to put to the screen, it's going to do a redraw. It queues this work with that. And so that happens it depends on the device. So 60 is kind of the gold standard, or kind of a regular monitor refresh rate. But it could happen at slower or faster refresh rates depending on the device. I think like an iPhone might be like 50 milliseconds or something like that. So it really helps because it basically pushes us off to the level that it ought to be, which is when the pixels are queued to put on the screen, that's when it happens. Are there any things that you guys are interested in terms of like actual draw calls? I didn't really do any. One of the things that's important is if you're doing sprite work, your draw image is your most expensive bit. So there are some tricks around kind of consolidating draw image calls. That's the main thing that you're going to be using if you're going to be putting image-based things on the screen. So you've got a sprite that's like a Pac-Man or a Mega Man or whatever else. That's actually like pixel art that comes from an image that you're blitting to the screen. And so you've got this draw image call that is actually expensive. And there's some tricks with caching or whatever that I would love to talk to anyone about afterwards that make that less expensive. Yep.
Are you drawing a single canvas and letting the canvas handle the double buffering?
So actually, the question was, am I drawing to a single canvas and letting canvas handle the double buffering? The answer is no, in general. In the code that I posted, it actually is just drawing to a single canvas. I'll edit that today so it actually double buffers in in-memory thing. So this is one of the bigger tricks that you can use is in this game loop, or in the renderer, you can actually create a canvas element that's off screen. So if you don't add this element to the document for real, it'll just sit off in memory. And so this is going along with the draw image kind of idea is that what you do is you use that as the back buffer. So on one frame, I'm taking all my entities and I'm making draw image calls to this in-memory buffer. And then I'm taking one draw image call, which is the entire buffer, and replacing the whole canvas that's on screen with it. So you've always got this kind of trading thing. So I'm putting everything in the in-memory buffer on one tick. Well, first I'm copying the things off the in-memory buffer. Then I'm putting all my single draw calls into this in-memory buffer, and then the next tick, I'm copying that whole thing again. And so you just do one call to the screen. Because draw image, if it's done to an in-memory canvas, is actually really fast. If it's done to the screen, it's expensive. Eric?
What tools do you use to figure out which part of your drawing is slow or?
That's a really good question. Eric asked, which tools do you use to figure out whether your drawing is slow? The tooling is terrible. It's really bad. Chrome, basically, Chrome DevTools. And so that you also have console.time, which you can wrap bits of your code in, and it'll actually time those little bits of code. But is this before? Is this earlier? This stuff, this new frame tool is really great, but it's really actually challenging to get good performance information. This is the best I've gotten so far. So this will actually, and this is in the dev branch of Chrome or Canary. This frame clicker guy will actually tell you how much time per frame was spent like rendering versus your calls, and you can actually kind of dig down to see if you've got an update problem. I think that's about it. Time-wise, I want to thank you guys for putting up with me. I put some CoffeeScript on the screen at 9 in the morning at the RubyConf, but I thought I would just, keep on with the thing of not doing Ruby at Cascadia. Thanks.